Okay, guys. Problem 4 is the last problem, and I think in some ways it's easier than problems 1 and 3 because you don't have to find all the forces in the truss. At the same time, though, it's more complicated because you do have to work with moments as opposed to axial forces, and moments are never as much fun to work with. I don't know if you guys find axial forces fun to work with, but I find axial forces much easier to deal with. So first things first, like always, you want to start off by finding your reactions. Where did my reactions sheet go? When you find the reactions, you're gonna get. Do I have it in here? Oh well, I can't seem to find my reactions right now. So, anyways, but you're gonna get reactions that are like this. Again, we're going to treat this like we did the number 3. Analyze it once, ignoring this load P here. Analyze it again, ignoring these 3 loads up here. To find when you're trying to analyze this, the easiest way to work with a sloped member is to just draw it out again. So I'm gonna, to get the moment in here, moment, shear, and axial forces in here, I would make my little cut. I would draw my moment diagram. And this would be for x going that way. Where do I have this second sheet here? Okay, so that is for x going that way. When I do that, I should end up getting, let me draw that out here. So my a of x will be my axial force, my shear force will be some fraction, or some will be due to this this reaction here. The easiest way for me to deal with this is to actually break it up into components. So you can imagine that instead of having a diagonal member, I actually have a flat member. I rotated too much. I actually have a flat member with member forces that are like this. And that is probably the easiest way to deal with this. So this is your, let me call this a y. This would become your ax prime, ay prime. I'm breaking up my vertical force into horizontal and vertical components along the diagonal. Then my v of x minus plus ay prime equals 0. V of x equals ay prime. My a of x plus ax prime equals 0. A of x equals negative ax prime. And my m of x equals ay prime times x, since x is going this way. So that is the easiest way to deal with that. That's for the diagonal member. For the other 2 members, just deal with it like you have before. So if I was interested in this section, it might be easier for me to go from right to left because I won't have to deal with these. I won't have to deal with this force and this force and this force. I only have to deal with, yeah, well, I find it easier to deal with this one. I cut it here. Shear is like this. My moment, my shear, my a of x. And again, I draw that out down here. So this is, I have reactions going this way. So my v of x2, m of x2, a of x2. This is dy dx. V of x2 plus dy equals 0. v of x2 equals negative dy. And my x is going from here. Or up on this diagram, it looks like it's going from here. This is my x2. My a of x2 equals dx. And my m of x2 is going to be, let's see, this one's causing, they're both causing rotation this way. And they're both going counterclockwise. They're going in the opposite direction of this. So they'll be equal to dx times 3 meters plus dy times x2. And I can do this again for this little number here. Yeah, so that is your shear axial force moment equations. The tricky part is just finding out how to break up this force. And I want you to be very careful about breaking that up. I will tell you that this problem, number 4, I am grading the even numbered homeworks. I will be grading number 4, so make sure that you do number 4 well, because number 4, I think number 4 is actually copied from last year's final exam. So that's, I think that is the case at least. And it was a very, number 4 was the problem that decided most of the grades for the course last year. Anyway, so you have all these equations. What do you do now? The next thing you need to do is the only reason why you did this is to get the diagrams. I'm not going to give you the diagrams because really important that you guys figure out how to graph these yourself. I will give you the shear diagram so you can check that at least. I will not be able to give you the moment diagram, however, because that is basically the fundamental thing you need for the problem. Shear diagram values that I have are 22 kilonewtons here, negative 12.5 kilonewtons here, and this one out here was 20 kilonewtons. I have this one being positive, negative, positive. Let me just double check. I'm sorry, this one was negative. So positive, negative, negative. That was my shear diagram. So this was A, B, C, and D. The main thing for this one, so you want to get your axial diagrams, get your axial, and get your moment. The axial one, you're going to analyze, once you have your axial force diagram, sorry, these are all your, this is all for the P system. You're going to do the same thing, you're going to get your axial and moment for your Q system, where the load is applied here at 1. A load of 1 is applied here. Same, sorry, this is pin, this is roller, pin, roller, pin, unit load of 1 here. So this will be your Q system. Get the axial forces due to a unit load here. Get the moment forces due to a unit load here. The same thing is happening as for number 3. Your P2 system, the forces and moments due to this load P will just be a multiple of these diagrams. You have a unit load of 1 here. Just multiply all the forces you get in here by P to get your P2 system. Your P2 system times your Q system will help you will give you the deflection at P. For this, recall that I think this is the last example he did in class, but for your deflection for a beam, you need to do deflection beam axial plus deflection beam bending. So this is due to axial forces. This is due to moments. To get your delta due to moments, you have this very, very helpful chart. You can do the analysis that the professor did in class. Break it up, break a trapezoid up into triangles, break a triangle up into more triangles, whatever you want to do. But this is a very helpful chart. Basically, your moment diagram is going to be composed of triangles or rectangles. In this case, because we have no distributed load, your moment diagram might look like this. I'm not sure what the moment diagram looks like, but you can imagine that your moment diagram might look something like this. This could be your, I don't know, your MP diagram, your MQ diagram. Let's call this M1, M2, M3, M4. Your MQ diagram might look something that is like, I don't know, like this. Something similar, but this might be a rectangle instead of being a trapezoid. So you might have, I don't know, M5, M6, M7. This would be your MQ diagram. You would have to look at each segment individually, but you just find the corresponding shapes on this table. So for example, my MP diagram is a triangle. My MQ diagram is a triangle. They're both triangles that have the tip at the same location. So when I'm going over here, I look at my MQ diagram first. My MQ is a triangle. My P diagram is a triangle. The tips are at the same location. I have to use this value. So the component of my, remember that I have to do a summation for every single member. I need to multiply, I need to take the integral of my MP, MQ on EI diagrams. I need to do this for every member. So for member AB, I said that I was going to use this formula, right? So my AB term is going to be 1/3. M1 is, it's going to be M1 times M5 divided by EI times L. I changed the number here because I'm using the value of the value M3 here is this value here. It's the height of my triangle. Okay, yeah, so I should have emailed this out to you. If I didn't email this out to you, then you can send me angry emails. And I'll be very sad, but I'll send it out again. Yes, and I think that's everything for this problem. I know I went through this very briefly, but it's very easy for a virtual work problem. It's very easy for a virtual work problem to require a very long explanation because there's a lot of work you have to do, and there's really no shortcuts other than using this table. With that, I think just be careful with the values that you're using. The tricky part with this problem is going to be getting the diagrams in the diagonal member, but once you have the diagrams, it should be fairly straightforward. Yeah, and I think that's everything. Don't forget to analyze both the axial and the bending. And if you have any questions, feel free to email one of us.